This is section 1.2. Today is going to be a little bit longer than last time. So a solution of a differential equation is simply a function that satisfies the differential equation on the interval given. So that's kind of a long definition for something that's very simple. Here's an example. Verify the equation y equals c e to the 3x plus 1 defines a one-parameter family of solutions of this differential equation. Now we know that when we solve a differential equation, we're going to pick up some constants. So we're not surprised to see a constant in our family of solutions. So we want to verify that this actually is a solution. So first of all, let's look at the left-hand side of this differential equation. So I have a left-hand side and a right-hand side, and I'm not going to assume they're equal. I'm going to show they're equal. Left-hand side is y prime. Okay, so here's y. I take the derivative. I get 3c e to the 3x. And the right-hand side is 3y minus 3. 3y is given as c e to the 3x plus 1. And I'm going to subtract 3. So let's simplify that. I get 3c e to the 3x. So the left-hand side is equal to the right-hand side. So yes, y is a solution. I verified it. Here's what you don't want to do. You don't want to assume the left-hand side is equal to the right-hand side. So this would be wrong. It would be wrong to say, well, the left-hand side is 3c e to the 3x. So put that in on the left. And then on the right, put 3y minus 3, which is 3c e to the 3x plus 1 minus 3. And then simplify this, and you get 3c e to the 3x on the left, and you get 3c e to the 3x on the right, and you say, oh, well, these are equal, and you move on. What's wrong with that, logically, is that from the get-go, you're assuming that the left is equal to the right, all right? You never want to assume what you're trying to show. And in your My Math Lab homework, they're not so good about separating out left-hand side and right-hand side, but you should be. So you should be better than them. Okay, find the particular solution that passes through the point x is 0, y is 3. All right, well, our solutions look like this. And so we just want to find the c so that will satisfy the curve passes through 0, 3. So I put 3 in for y and 0 in for x. E to the 0 is 1, so I get c is 2. And so the solution I want is y equals 2 e to the 3x plus 1. And that is called a solution to the initial value problem, and it's a differential equation plus an initial condition. All right, now you try one. Pause the video and determine if this function is a solution of this differential equation. And then when you're done, restart the video and we'll do it together. All right, hopefully you did that. In this equation, I see a second derivative, so I'm going to do some preliminary work. I'm going to say, all right, if y is this, then y prime is cos x plus 2x, and y double prime is negative sine x plus 2. So now I can look at this differential equation. The left-hand side is y double prime plus y. So that's negative sine x plus 2 plus y is sine x plus x squared. So that simplifies to x squared plus 2. And the right-hand side of the equation is x squared plus 2. So I see right away that the left-hand side is equal to the right-hand side. So yes, I have a solution. Let's do a slightly harder one. We want to show that this equation here implicitly defines a solution of this differential equation. So here I can't solve for y to get y prime. So I'm going to need to use implicit differentiation first to solve for y prime. Let's just remember how that goes. I want to take d by dx of both sides of this equation, and I'm going to treat x as x, but y is a function of x. So when I take the derivative of e to the xy, I copy down e to the xy, but in front, I put the derivative of the exponent. The derivative of the exponent requires the product rule. The derivative of x is 1. 1 times y is y. And then I take x times the derivative of y, which is just y prime. So all of that is the derivative with respect to x of e to the xy. Then I add on d by dx of y, which is y prime. And I set that equal to the derivative with respect to x of x is 1. Now I want to solve for y prime. So we need to distribute y e to the x y plus xy prime e to the xy plus y prime equals 1. So I want to factor a y prime out of the two terms here, x e to the xy plus 1. And then take this term, since it doesn't have a y prime in it, I want to move it to the other side. 1 minus ye to the xy. Finally, I'm going to divide by this expression here to solve for y prime. Y prime is 1 minus y e to the xy over 1 plus x e to the xy. That is the left-hand side of this differential equation. What's the right-hand side? It's e to the negative xy minus y over e to the negative xy plus x. Now, before you just say, oh, left-hand side is not equal to right-hand side, pause a minute. Maybe it is. What if I took the right-hand side and I multiplied by 1, but I wrote 1 as e to the xy over e to the xy? Then what I would get is 1 minus y e to the xy over 1 plus x e to the xy. Oh, left-hand side is equal to right-hand side. So yes, we did what we were supposed to do. We showed that we had a solution. Okay, for what values of m is the function y equals e to the mx a solution of this differential equation? So we need to do some preliminary work. Y is e to the mx, so y prime would be m e to the mx. Y double prime, bring another m down, m squared e to the mx. So for y to be a solution, we would need y double prime, which is m squared e to the mx, minus 5y prime, y prime is m e to the mx, plus 6y plus 6 e to the mx. That would have to be 0 for all x. Okay, well, e to the mx is never 0. Let's pull that out. So we get m squared minus 5m plus 6 equals 0. So this is 0 for all x if and only if m squared minus 5m plus 6 is 0, because e to the mx is never 0. And so this is m minus 2, m minus 3 has to be 0. So we see that m is either 2 or 3. Pause the video and try this one. Okay, this one's slightly different. Hopefully you got m equals -2 and 4. If not, let's see what you did wrong. If y is x to the m, then y prime, okay, different derivative rule. Now I'm using the power rule. Bring the m down and subtract 1 from the exponent. And y double prime, bring the m minus 1 down, subtract 1 from the exponent, I get m minus 2. I still need this equation to be true. So that's x squared. And then in place of y double prime, I'm going to put m times m minus 1, x to the m minus 2, and then minus x, and in place of y prime, I put m x to the m minus 1, and then minus 8x to the m. That should be 0 for all x. Okay, if you distribute this guy to this guy and this guy to this guy, then what you'll see is that each term has an x to the m in it. Each of the three terms has an x to the m in it. So I'm going to pull that out. What's left is m times m minus 1 minus m minus 8. That has to be 0 for all x. So that means x to the m. Now let's expand this. This is m squared minus 2m minus 8, that's 0 for all x, if and only if, or this implies that this guy has to be 0. And let's factor that guy. That's m minus 4, plus 2, that's 0. So that's how I got -2 and 4. All right, last topic of the day, the EUT. An IVP is a differential equation and an initial condition. If you have a first order IVP, you need to be told to uniquely determine the solution curve what point your solution passes through. So you'll have a family of solutions, maybe y equal x squared plus c. And if you're given what point the solution curve passes through, you can determine c. And so you'll have one initial condition. For a second order, you're going to need two initial conditions. Well, it's one initial condition, but it's two equations. First of all, you need to know what point the curve passes through. Y of x naught is y naught. Second, you need to know the slope of that curve as it passes through that point. So in one of the examples above, we saw that y equals 2e to the 3x plus 1 was a solution to this IVP. That raises two questions. One, is it the only solution? That's uniqueness. Two, did we know that existed from the get-go? Were we trying to find something perhaps that didn't exist? So together, those form existence and uniqueness. We want to know our solution exists. If it does, we want to know it's unique. So we have one of many EUTs in this course. This is existence and uniqueness theorem 1, EUT, for a first-order differential equation of the form y prime is f of xy and y of x naught equals y naught. So the theorem goes, as long as two conditions are met, you will have guaranteed a unique solution in some interval around the point x naught, y naught. And the conditions are, the function f has to be continuous for all x, y in a little rectangle around that point. It doesn't matter how small, it can be tiny. It actually doesn't have to be a rectangle either, it could be a circle. That's condition 1. And condition 2 is the partial of f with respect to y is also continuous in a little rectangle around the point in question. So let's see how this works. Determine whether the EUT implies that the given IVP has a unique solution. Which condition passes and which fails? So our first differential equation looks like this. In order to use the EUT, we need to make it look like this. Y prime equals f of xy, y of x naught is y naught. So if we solve for y prime, we're going to multiply both sides by x, we get y to the 1/3 times x, and the x naught, y naught is when x is 2, y is 0. So this is the point 2, 0. I plotted that point right here. The first thing you want to do when you're using the EUT is identify f and identify the point in question. I like to write it as an ordered pair rather than y of, in this case, 2 is 0. So our f in this case is y to the 1/3 times x. So condition 1, f of xy, you can just write f, but if you want to be fancy, write f of xy equals y to the 1/3 times x. All right, the question is that continuous for all xy in a little rectangle around the point 2, 0? Well, this is continuous everywhere. So all xy, so it's certainly continuous in a little rectangle around the point 2, 0. So continuous for all xy, so it's certainly continuous around, put that in quotes because it's a little vague, but I mean for all xy around the point 2, 0, around 2, 0. So yes, this guy's a check. Condition 1 is met. Condition 2, f sub y is 1/3 y to the negative 2/3 times x. Let's rewrite that. That's x over 3y to the 2/3. This is not even continuous at 2, 0. This is not continuous when y is 0. So at 2, 0, it's not continuous. So it certainly could not be continuous in all xy around that point if it's not even continuous at that point. So not continuous around 2, 0. So this is a fail. So does the EUT apply? No. If one of the conditions fails, you can't even use the EUT. So the condition that failed was condition 2. So let me be clear. This is not saying I don't have a unique solution at 2, 0. I might. I'm just saying that the EUT does not guarantee that I do have a unique solution around at that point. Okay, next one. Condition 1, f of x, y. So if I solve this for y prime, I get 4x over y. So that's my f. And my point is 1, 0. So x is 1, y is 0. That's here. This is not continuous at 1, 0. So definitely not continuous around 1, 0. So this is a no. In order for this function to be continuous, I need to be at a point that's well away from, well, not well away, but away from the x-axis. So if this EUT was up here at this point, yeah, as long as I stay away from the x-axis, I'm okay. Unfortunately, I'm on the x-axis, so there's no way I'm going to be able to be continuous around that point. Condition 2 is almost irrelevant because as long as condition 1 fails, we know the EUT doesn't apply, but let's just check it anyway. F sub y, it's good practice with partial derivatives. So this would be negative 4x over y squared. This is also not continuous around 1, 0. So this is a failure. So this is no, and they both fail. Okay, and that is the end of this lecture.